The carbon-fluorine bond is the strongest structure in organic chemistry. Requiring extreme heat or massive energy to break, it drives the PFAS crisis. Because this artificial bond is evolutionarily novel, biological systems haven't evolved a single-step enzyme to digest it. We are currently dealing with between 5,000 and 10,000 variants of PFAS. Analyzing and regulating these substances on an individual basis is mathematically impossible. Dr. Linda Birnbaum's toxicology research demonstrates that these chemicals must be regulated comprehensively as a single class. Her work indicates policy must protect sensitive developmental windows, such as pregnancy and early childhood, rather than focusing on average lifetime exposure. Because we cannot regulate these chemicals individually, nor rely on natural evolution to break them down, environmental engineering requires a hybrid architecture to manage them. Commercial startups frequently claim to have discovered a single supermicrobe engineered to completely mineralize PFAS on its own. The strict thermodynamic reality of the carbon-fluorine bond makes that single microbe model functionally impossible for large-scale industrial remediation. When unadapted, isolated commercial bacteria are introduced into complex, highly contaminated waste environments, the process routinely fails. Biological remediation depends on interspecies microbial syntrophy. Specific ecosystem engineers must prepare the chemical environment first, allowing dehalogenating operators to execute the reaction. Unlocking that complex microbiology requires first minimizing the chemical load using a strict physical and regulatory framework. This diagram illustrates a 5-layer remediation funnel. Layer 1 is prevention. Statistically, the most cost-effective solution is supply chain exclusion. Layer 2 is protection. We must implement policies that shield sensitive populations, like infants and pregnant women. Layer 3 is concentration. Active carbon and foam fractionation capture the chemical load, but simply move the PFAS to a new location. Layer 4 is physical destruction. Breaking the CF bond using external energy is a prerequisite for biological processing. Japanese universities have recently advanced this layer by demonstrating photocatalytic cleavage. By using visible light and semiconductor nanocrystals, they can sever the carbon-fluorine bond at ambient temperatures. Only by utilizing these top 4 layers to concentrate and physically weaken the chemical load does the 5th layer, bioremediation, become mathematically viable. Bioremediation, layer 5, acts as a highly specific pre- and post-treatment processor for fragmented molecules, rather than a direct mineralizer of virgin PFAS. The primary industrial theater for this biological processing is the standard anaerobic digester, already used globally for livestock and industrial waste. Agricultural waste operates on a massive scale. PFAS tepicals from various streams accumulate here and mix with exceptionally high levels of organic matter. These anaerobic digesters are naturally dominated by methanogenic archaea, an entirely different domain of life that dictates the chemical potential of the environment. Effectively using biology to break down PFAS requires engineers to move beyond isolated bacteria and focus on cultivating the archaeal ecosystems they depend on. In these systems, archaea function as ecosystem engineers, manipulating the local chemistry to support specific bacterial reactions. This diagram illustrates their first function, redox maintenance. Archaea continuously consume ambient hydrogen, maintaining the low oxidation reduction potential required for defluorination. Their second function is biosorption. S-layer glycoproteins carry a negative charge, concentrating PFAS molecules on their surface. Their most critical function is cofactor supply. Bacterial reductive dehalogenase enzymes remain inactive without coronoids, specifically vitamin B12, which the bacteria cannot synthesize independently. Methanogenic archaea synthesize this B12 internally and transfer it directly to neighboring dehalogenating bacteria. Archaea provide the necessary biochemical infrastructure and essential cofactors, without which bacterial dehalogenation remains thermodynamically blocked. Within this engineered environment, bacterial operators like D. halicocoides and Acidimicrobium strain A6, known as Phaemox, can begin to function. The bacteria absorb the archaeal B12 and incorporate it into their RDHA-derived enzymes to initiate the reaction. The activated enzyme then breaks the carbon-fluorine bond, releasing a single fluoride ion from the chain. For Phaemox strains, this defluorination speed is directly proportional to ammonium oxidation, allowing the process to integrate with existing agricultural nitrogen cycles. This precise division of labor, archaeal engineering combined with bacterial operation, is the basis of functional biological remediation. Returning to industrial operations, livestock waste and industrial effluents are processed in massive volumes. Monitoring baseline PFAS reduction in these massive tanks provides an insufficient diagnostic tool for engineers. This dashboard readout plots the 3 critical metrics required for oversight: ambient B12 concentrations, D-halocochides populations, and PHMOX activity via iron-3 addition. Strict new legal obligations for continuous water quality testing will soon mandate this level of granular, continuous data. Successfully managing an industrial digester for PFAS remediation now requires the precise cultivation of a fragile archaeal ecosystem. Following Dr. Birnbaum's principle of scientific integrity, environmental professionals must provide accurate assessments of biological capabilities to the public. Biologically cutting a PFAS molecule into shorter chains does not result in harmless mineralization. The toxicity of intermediate byproducts must always be evaluated. Solving the PFAS crisis requires executing the full 5-layer pipeline: strict regulatory prevention, physical chemistry, and the exact biochemical syntrophy between archaea and bacteria. The remediation of these chemicals depends on a rigorous multidisciplinary engineering framework rather than any single biological discovery.